Hey everyone, welcome to Recitation 14 on deep reinforcement learning. My name is Vedant and I'm going to be taking you through this recitation. So first, these are the goals we have for this recitation is we want to introduce reinforcement learning and explain how it's different from supervised learning, which is mainly what you've been working with through the semester. And secondly, we want to discuss how the field's really developed over time. We'll discuss some dynamic programming methods that aren't used that much anymore, and how these methods evolved to the point where now we have deep Q networks. And then finally, we're going to explain some of the problems that were actually solved in the research paper and how they were able to get neural networks to work in reinforcement learning. So what this recitation is not going to do is cover all the algorithms we discuss in depth and really explain how they work. We do have pseudocode up on the slides, but that's mainly just to facilitate your understanding. We just kind of want to motivate why, how the field really came about and how it evolved, but we're not going to discuss how these algorithms work in depth. So this is a really nice textbook that I found, which I used a lot to learn more about the field. And a lot of the pseudocode on the slides is borrowed from this textbook. So if you want to learn more or just study something more in depth, I would highly recommend this textbook. Okay, so what is reinforcement learning exactly? So there's one fundamental question that we're trying to answer, and it's what to do, and more specifically, what to do given a current state. So we're trying to map states to actions, and what we're doing to motivate that is we're trying to maximize a certain reward signal. So there's two defining characteristics you can think of, which is trial and error search. We're actually interacting with the environment to get certain rewards, and delayed reward, which is that we also take into account rewards that aren't immediate from one transition, but also like further down the line in time. So how is it different from supervised learning? Well, in supervised learning, we have a data set which is labeled, as in we have the inputs and the corresponding outputs. And the goal is to learn a function that can accurately predict the outputs given the new inputs. In reinforcement learning, and this is where one of the key things comes in, there is no labeled data set. So we're relying heavily on the reward signal, or how it says in the slides, feedback. So these are the key components of an reinforcement learning problem. So we have the agent, which is the decision maker, and the agent is what's learning here. We have the environment, which is what the agent is interacting with. We have a state, which is a representation of the environment, which is given to the agent. A state space is just a set which consists of all possible states. Action is what the agent uses to interact with the environment. An action space is just a set of all possible actions it could take. So if you were playing a game and your character can move forward, left, right, and back, your action space would be of size 4. And then the reward, which is a signal which the environment gives the agent based on a particular transition. So to introduce some terminology here, a trajectory is, you can think of it as almost like a tuple or a list, which consists of the current state, the action taken at that current time step, and then the reward observed from taking that action at that state, and then the next state, which is a result of taking that particular action. So this is pretty intuitive and it's easy to understand. You have a current state at a particular time t, you take an action at that time, you receive a reward for taking that action, and then you find yourself in the next state. And this is really how the agent and the environment communicate with each other. So a sequence of these tuples, you can think of them as a trajectory. And when the trajectory ends in a terminal state, we call that an episode from start to finish. So exploration versus exploitation is just a quick note I wanted to mention. So this is a big thing that needs to be balanced in reinforcement learning, because once your agent starts to learn a policy, there's a trade-off between continuing to exploit what you know and following that policy, what has like the highest rewards, returns, or values, versus exploring states you haven't seen before. Because when you explore new states, you can find policies that lead to better long-term outcomes. So one popular and pretty simple method to balance these two is called an epsilon greedy action selection method. So epsilon you can think of as a certain probability, and it's the probability that you're going to explore or choose an action randomly. And with probability 1 minus epsilon, you're going to follow your policy and act greedily. So the first kind of reinforcement learning algorithms you'd learn is those are of the family of dynamic programming. And it's when we pose a problem as a Markov decision process and we can compute optimal policies. But the caveat here is that we need a perfect model of the environment. Now, this family of reinforcement learning algorithms isn't used that much in practicality because one, we can't assume a perfect model of the environment. That's hard to come by in reality. And second, it's computationally very expensive. So one of the most popular ones is value iteration. And what we're trying to do in value iteration is come up with accurate values for each state. And a value basically represents the expected total reward that an agent can get starting from the given state and then following the policy thereafter. So this is really where that theme of delayed rewards comes in as well. We're also accounting for that. So this is the Bellman update, which is how we update the value on each iteration. And I've just listed out some terminology that the equation uses here, and we'll go over what the update means. So the probability we're using here is called a transition probability. And it's the probability that we'll observe the next state and the reward, given that we're in state S and we take a particular action. So this is when we model the environment with that's non-deterministic. So if you're in a certain game, let's say, and you move your character forward, there isn't 100% probability that they actually will move forward. So this is to account for that. This term in the red box here is the reward that you get for taking that particular action, that particular state. And we also have a discount factor here called gamma. Now, gamma will usually be a number between 0 and 1, and we use it to discount future rewards because we want to prioritize immediate rewards more. And we're taking a max over all possible actions you can take from the current state. So once you understand what the Bellman update is doing, then the actual value iteration algorithm isn't that complex. You're just looping over all the states, and until convergence, you're performing Bellman updates on every state. So given the fact that dynamic programming based methods aren't that practical because we don't have complete knowledge of the environment, and for large state spaces, looping over all the states is computationally very expensive. We have a family of methods called Monte Carlo methods, which come into place. So this family of methods is a big improvement over our previous ones because we don't need perfect knowledge of the environment. In fact, we don't need any prior knowledge of the environment's dynamics. We just need experience in the form of trajectories. And I won't go into depth into how the algorithm works, but the key idea here is that we follow a trajectory to completion, so a complete episode, and then we update the values based on the average rewards we get. So the two key things here is we're averaging the rewards over the entire episode, basically, and we're also only performing the update once the episode ends completely. So Monte Carlo control is just the process of using this method to get an optimal policy. And this is done through a process of generalized policy iteration. So the next improvement from Monte Carlo methods came in the form of temporal difference learning. And this is similar to Monte Carlo methods in the sense that we still use experiences that our agent gathers from interactions with the environment. But the key difference here is that one, we use something called bootstrapping, which means that to update the value function, we use a combination of the actual reward we get and an estimated value of the next state. So we're using an estimate to update the current value function as well. And that's something called bootstrapping. And the second key change is that we don't wait for an episode to go to completion. We can do this incrementally at each time step. So the reason we spoke about dynamic programming based methods and then Monte Carlo methods and then temporal difference methods is because Q learning is a specific is part of the family of temporal difference learning. And essentially what we're trying to do here is learn the Q values directly. Now, remember from the earlier slides on value iteration that each state has a value which tends to represent its long-term rewards. So it's a similar concept with Q values, but except for assigning it to each state, we assign these to each state and action pair. And this is the update rule used for Q learning. Again, you can see the bootstrapping we have here. This is the algorithm. Again, nothing too complicated once you understand the update rule. And now we can start to think about how neural networks can help this process or where they would fit in. So we spoke about how Q values are assigned to a state and action pair. So if we have a large number of states or a large state space or a large action space, then storing Q values for each state and action pair would become pretty impractical. And using neural networks would allow us to approximate Q values for each state action pair without explicitly storing them. So it would save us a lot in terms of storage. And another benefit we get is that neural networks tend to generalize well, which means that once we have estimates for particular states and actions, they can generalize to similar states that haven't been visited, or even in cases where the state space is continuous. So when we're training neural networks, we need to compute a loss, which we backpropagate. But what exactly would that loss be? And it's a mean squared error loss between the target Q value, which is the reward, plus the discounted target Q value, and our prediction for the Q value. Now that sounds like a really good setup, and we can clearly see the need for Q networks and how it would really help the process and save us a lot of memory. But there are some issues with training. So one is that when we're training, our targets are constantly changing, and it's called like a moving target. So the target Q values are also output by a neural network, and our predicted Q values are also output by a neural network. So when we're training and we're updating our weights and parameters, then our target is constantly changing or our label is constantly changing. And this leads to a lot of instability in training. Another issue is that there's a correlation between samples. So when the agent interacts with the environment to create a trajectory or an episode, it generates a sequence of experiences that are highly correlated in time. And if the neural network is trained on these consecutive experiences, it can learn to overfit a specific sequence and fail to generalize the new experiences, which was one of the key reasons we're trying to use a neural network here. So the solution to both of these problems came in the DQN paper, which I've linked over here if you want to read through it. And they solved the moving target problem by using two separate networks, a target network and a predictor network. And they solved the problem of correlated samples using something called experience replay. So the way having two separate networks works is we have a target network, which we keep the weights fixed for a certain K number of iterations. That's a hyperparameter you can tune. And we have a prediction network, which is constantly training and updating. So every certain iterations, we update the target network to have the same weights as the prediction network. So this is a way we can have an accurate network that's updating, but it reduces the instability associated with the moving target. And the way we deal with the correlated samples is that we store all the agent's experiences in a data set. And you can see this in the form of the state, action, reward, and next state tuples we were talking about earlier. And during training, we'd actually sample random mini batches from our data set. So our training samples wouldn't be correlated anymore. So yeah, this is essentially how they tackle the two major problems associated with training neural networks. And this is how they really got it to work. So this was really revolutionary paper. So this is the end of my section. And I know we didn't go into too much detail into how the algorithms work, but I hope I've given you some sense of intuition as to how this field evolved and the problems associated with using neural networks in reinforcement learning and how these were overcome. Thank you so much.